AP Chemistry, Lesson 7, Ionic Bonds. So this begins a two-lesson set on the three types of chemical bonds. So there are 90 naturally occurring elements on the periodic table, and they combine to form millions and millions, even tens of millions of compounds. Chemical bonds are central to chemistry because they are how atoms are joined to create new compounds. Even so, there are only three ways elements combine. Ionic bonds: an atom passes electrons to another atom. Covalent bonds: atoms share electrons. Metallic bonds: electrons jump from atom to atom like frogs on lily pads. To me, there's two amazing facts about chemistry. One is that there's only 90 natural elements in the entire universe. You can fit them all on a single piece of paper. We call that the periodic table. That's one of the two amazing facts. The other one is they form tens of millions of compounds. Those 90 natural occurring elements can form tens and tens of millions of compounds by bonding together, by creating chemical bonds. And yet there's only three types of chemical bonds. There's only three ways that they bond together. So only 90 elements, only three different ways that they connect with each other, called chemical bonds, creates every substance that there is in the universe. So the octet rule is really one of the most important rules in chemistry. And the octet rule says that atoms are in their most energetically favorable state, and sometimes we just use the metaphor that they're happy. They like to be in that state. They're in their most energetically favorable state when they can fill their valence orbital. Octet means 8. It's called octet because all elements need 8 electrons to fill their valence orbital, the only exception being hydrogen and helium in the first period of the periodic table. So the elements that are born with full octets are called noble gases, and they're called noble, and bring those up, they're called noble because they're like royalty. Other elements want to be like them. So noble gases such as helium and neon at the end of the periodic table on the right hand side already have full valence orbitals. So in the case of helium, the first orbital can only hold 2 electrons. They still call it the octet rule even though it's only 2 electrons because it does have a full valence orbital. Neon and everything below neon actually has a full orbital of 8 electrons and has a full octet of 8 electrons in its valence orbital. So that would be neon, argon, krypton, radon, on down the right hand side of the periodic table. So the octet rule for metals. So all atoms want to be like noble gases. They want to have a full valence orbital. Now you can see lithium's valence orbital is the second orbital. And it only has 1 electron. If it wanted to fill that up with 8 electrons, it would have to add 7 more. So lithium could gain 7 electrons to have a full second orbital like neon. However, we learned that lithium, being way over on the left side of the periodic table, has a very low electronegativity. And therefore it doesn't pull in electrons easily. So it's not going to do that. It's physically impossible for it to even pull in 1 electron, let alone 7 more. So lithium wants to be like that guy way over on the right, neon. It would have to add 7 electrons. Or here's another way. It kind of fills a valence orbital through the back door, kind of a sneaky way here. Or lithium can lose its second orbital electron and have a full first orbital like helium. So you watch there, instead of the arrow going to neon, it's going up to helium. So lithium gives away that electron. When it gives away that electron, that's no longer its valence orbital because it no longer has any electrons in the second orbital. And so now it has a full valence orbital. Its first orbital becomes its valence orbital, and it has a full valence orbital just like helium. So that explains, at least in principle, why does it have a low ionization energy? Why does it easily give up that electron, and it has a low ionization energy because it wants to be like the nearest noble gas. The nearest noble gas to lithium is not neon in its own row in the second row. It's helium one row behind it. So conclusion, the easiest way for lithium to be like a noble gas is to lose one electron and have a full first orbital like helium. So now let's look at the octet rule for nonmetals. And these are the orange elements, as well as the halogens, which are the dark green elements, fluorine, chlorine, bromine. We don't count the noble gases as part of those. So there's not very many nonmetals, yet as we mentioned earlier, they're very important because your body is made up almost entirely of nonmetals. So all atoms want to be like a noble gas and have a full valence orbital, full outer orbital. Fluorine has an easier way. The nearest noble gas is neon right next door. So if you look at F, the nearest noble gas is right next door, neon. So if fluorine can have a full second orbital simply by picking up one electron. Now, is this possible? Well, sure. We talked about that fluorine has a high electronegativity. It likes to pull in outside electrons. It's very good at doing that. So it can, unlike lithium, which can't pull in outside electrons, fluorine can very easily pull in one more outside electron to fill that empty space that you see and give it a full octet. And there it is. So fluorine has a full octet. Now, do you really need to understand deeply, like a professional chemist, why does the octet rule work? Why do things want to form octets? You don't. You just have to understand what was said in the previous slide. It's the most energetically stable state. You don't have to understand it any deeper than that. So don't worry, you're not asked to explain why is 8 electrons the most energetically stable. You can just accept it as gospel, as the truth here at this level of chemistry, even at the AP level, at the basic college level, that atoms want to form octets. They're more energetically stable when they can have a full valence orbital. So conclusion, fluorine gains 1 electron to give it a full second valence orbital with 8 electrons. So let's talk about the ionic bonds that form cations. So alkali metals, alkaline earth metals, and transition metals, and boron is a metalloid actually, have low ionization energies and more easily give up electrons. So everything you see there in green will give up electrons easily and form a cation. Remember, when they give up electrons, that means they have more protons than electrons, and that means that they have a positive charge. So they become positive, like little positively charged magnets, except it's not magnetic, it's electrical, but they have a charge on them. All of those that you see in green will give up electrons. They won't take in electrons, they'll give up electrons. Metals, which become cations, that's positively charged ions, are shown in green below. Bond with anything. Okay, ionic bond anions. So nonmetals have high electronegativities, so they can gain electrons. Nonmetals can most easily complete a valence orbital octet by adding electrons. So nonmetals, which become anions, negatively charged ions, are shown in blue. So since they gain electrons, they'll have more electrons than protons, and that will give them a negative charge and make them an anion. So the halogens, that's the group in blue furthest to the right, that's fluorine, chlorine, bromine, they need to gain 1 electron to be like the nearest noble gas and have a full valence orbital with 8 electrons. The chalcogens, that's a term that's almost never used, but that's the group, the column with oxygen in it. So oxygen, sulfur, selenium. They gain 2 electrons, and that gives them 8 electrons in their valence orbital. And then they're like the nearest noble gas. And then nitrogen, phosphorus, arsenic, they can be like the nearest noble gas by adding 3 electrons to their valence orbital so that they have 8. The elements in red are 4. They can either add 4 or add 4 or lose 4 electrons to be like a noble gas. The fact is that those elements in red never form ionic bonds. They form covalent bonds, which we'll study in a later lesson. So the elements in red can either take on a positive or a negative charge. And the noble gases already have full octets. They do not want to gain or lose electrons. There's a term for that. It's called inert. They don't like to react because they don't like to give up electrons or take in electrons, so they tend to not be reactive. There are some exceptions to that. We'll talk about those later. So let's take a more detailed look at that and be sure we really have this concept understood. So lithium, which is way over on the far left side of the second period, second row, lithium can have a complete octet by filling its second orbital. This would require adding 7 electrons. Since lithium has a low electronegativity, that is, it doesn't like to pull in electrons, this would be impossible. It is easier for lithium to give up one second orbital electron, as well as the second orbital. This means that lithium would have a filled first orbital, the same as helium. So lithium loses 1 electron, giving it a 1+ charge. Okay, beryllium. That's the element right next to lithium in the second row. It can have a complete octet by filling its second orbital. This would require adding 6 electrons. Since beryllium also has a low electronegativity, this would be impossible. It's easier for beryllium to give up its two second orbital electrons as well as the second orbital. This means that beryllium would have a filled first orbital, the same as helium. So beryllium loses 2 electrons, giving it a 2+ charge. 2+ meaning it has 2 more protons now than electrons because it gave up 2 of its electrons. Boron. Boron is the third element over from the left in the second row. Boron can have a complete octet by filling its second orbital. This would require adding 5 electrons. Since boron has a low electronegativity, its electronegativity is higher than lithium or beryllium, but it's still pretty low. This would be impossible. It is easier for boron to give up its 3 second orbital electrons as well as the second orbital. This means that boron would have a filled first orbital, the same as helium. So boron loses 3 electrons, so it now has 3 more protons than electrons, so we say that it has a 3+ charge. Okay, carbon can fill an orbital by gaining 4 electrons or losing 4 electrons. Generally, carbon doesn't ionize. Now we're going to go on over to the right side of the second row. So nitrogen can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require that nitrogen lose 5 electrons so that it has a full first orbital identical to helium. But you notice nitrogen is closer to the right side of the periodic table. It's closer to neon than it is to helium. So it's easier for nitrogen to add 3 electrons, giving it a filled second orbital. Now you're getting into elements that have higher electronegativities that are able to pull in electrons from the outside. And this creates the electron configuration of neon. So nitrogen gains 3 electrons to fill its octet, its outer orbital, and therefore we say that nitrogen has a 3- charge, meaning 3 more negative charges, electrons, than protons. Oxygen can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require that oxygen lose 6 electrons so that it has a full first orbital identical to helium. It's easier for oxygen to add 2 electrons, giving it a filled second orbital. This creates the electron configuration of neon. So it gains those 2 electrons, has a full octet. So oxygen gains 2 electrons, giving it a 2- charge, 2 more electrons than protons. Fluorine can have a complete octet by giving up electrons as lithium, beryllium, and boron did. This would require fluorine to lose 7 electrons so that it has a full first orbital identical to helium. Well, it's not going to do that. It has a very high ionization energy. It's not going to lose electrons. So it's easier for fluorine to add 1 electron, giving it a filled second orbital. This creates the electron configuration of neon. So fluorine gains 1 electron, giving it a 1- charge, 1 more electron than proton. Okay, this is a periodic table of charge numbers. You'll be getting a sheet that looks just like this. It shows you the charges that various elements will take on. So if we go to the second row, we see lithium has they just put a plus sign, but it's a 1+. Beryllium a 2+. You go across, they don't show boron. Well, they do up above, excuse me. Boron has it's really a 3+ charge. Carbon doesn't show as having a charge in either direction. And then nitrogen is 3-, oxygen is 2-, and fluorine is 1-. So that's the ones we just covered. And you can see what they are for other elements. You'll notice, for example, that all the elements in the halogen group, that is the same one as fluorine, also have 1- charges. They all want to gain 1 electron to become like the nearest noble gas. And you'll see that over on the left-hand side, that everything in the alkali metal group, that would be lithium, sodium, potassium, LiNaK, have 1+ charges. Everything in the alkaline earth group, alkaline earth metal group, would have a 2+. That would be beryllium, magnesium, calcium, and so on. So those are the easy ones. The ones that get a little trickier are the ones in the middle. Look at the transition metals and some of the other metals over there below the nonmetals. You'll notice that many of those have more than 1 charge state. You're not expected to memorize those. That's why you'll have this table. You should know the ones for the first 2 columns and for the nonmetals, how to figure out what those are going to be, what we just spent the last few slides doing. But for the others that are in the transition metals, for example, iron is number 26, Fe. It can either have a 2+ or a 3+. In other words, it can either lose 2 electrons or 3 electrons. And in fact, it actually has about 5 or 6 different charge states, but we'll never use any of the other ones, or I would say almost never. So it has 2 different charge states. Copper, Cu, has a 1+ or a 2+. Silver, Au, has a 1+ or a 3+. So you can see that there's different charge states for those. So that's the transition metals will have these different charge states. So you use this table. So certain ones of these you'll have memorized, like iron and copper, for example. But you're not expected to memorize all of those different charge states. So here's some examples. Iron can lose either 2 or 3 electrons, giving it a 2+ or 3+ charge. Copper can lose either 1 or 2 electrons, giving it a 1+ or 2+ charge. Sn is tin. Tin can lose either 2 or 4 electrons, giving it a 2+ or 4+ charge. And lead, Pb, can lose either 2 or 4 electrons, giving it a 2+ or a 4+ charge. One thing to keep in mind is that metals always become cations. They never take on electrons, they always lose electrons. Okay, so here's a part of another table that you're going to be given. It's called the 60 common ions. And it has several different sections, 4 different sections to it. Here are the top 2. So the top one is kind of the most basic one. It shows the ones that we kind of looked at, the ones that are either in the alkali or alkaline earth metals, the 2 left columns, or the last 3 columns on the right before the noble gases, and those either become positive or cations or negative anions. Down below you'll see some of the ones we just talked about in the transition metals that can have more than 1 charge, such as copper, lead, iron. There's also mercury there, and anyway, so you'll be getting a sheet of these. No reason to memorize these at this time. So let's learn how an ionic bond works. You've learned about ions and cations and anions. So here's a simple explanation. Ionic bonds result when when an atom transfers an electron to another atom. So you just saw the electron transfer from the lithium to the fluorine. Why did that happen? Because lithium has a low ionization energy. It's easy to take its electron away from it. And fluorine has a high electronegativity, so it likes to take electrons away. I refer to fluorine as one of the strong guys. Lithium is one of the weak guys. So it will pass an electron over. So the atom that lost the electron becomes a positively charged cation. That would be lithium in this case. And the atom that gained the electron becomes a negatively charged anion. That would be fluorine. The positively and negatively charged atoms attract each other to form an ionic bond. So ionic bonds must be electrically neutral. So one of the atoms or one of the ions is positive, one's negative, but when you put them together, they neutralize each other and become electrically neutral. One positive, one negative. The smallest unit of an ionic bond is called a crystal lattice structure, and it looks like that. And you can think of it like bricks in a wall, but it kind of explains why ionic bonded substances such as salt, table salt, looks like they're in little cubes, is because they will form this relationship that looks like this. So the smallest unit of a crystal lattice structure is called a unit cell or formula unit. So in the case of lithium fluoride, if this is lithium fluoride, there's one lithium for every fluorine. So you'll notice one purple sphere for every green sphere. It's a one-to-one relationship. What you'll notice though is if you look at that purple sphere in the front, in the middle, which green sphere does it belong to? The one on the top, the one on the bottom of it, the one to the left side, the one to the right side? The answer is it belongs to all of them. So even though it's a one-to-one relationship, and we would call this compound lithium fluoride, that purple lithium sphere is bonded to all of the fluorines around it. And so it's shared by all of them. It doesn't just belong to one of them. So lithium fluoride, LiF, is an example of a formula unit. Okay, atoms that give up electrons easily are usually alkali metals, alkaline earth, those are the two columns on the left, 1A and 2A, or transition metals, that's the valley in the middle, the ones with the red letters and red symbols there. These elements have low ionization energy, so they easily give up electrons. So those and those. Those are the ones that are going to give up electrons. Also, some of the other metals just to the right of zinc, cadmium, and mercury, like gallium, germanium, indium, they also give up electrons. Go back to the periodic table of charges a few slides back, and you'll see the ones that have pluses are the ones that give up electrons. So the atoms that attract electrons are usually nonmetals, particularly halogens. So these elements have high electronegativity, so they strongly attract electrons, the ones that you see there in green. Okay, when lithium and fluorine get together, lithium gives up one of its valence electrons to fluorine, like that. Lithium has low ionization energy, which means it easily gives up its second orbital electron. It doesn't take very much energy to take away that second orbital electron. Fluorine has a high electronegativity, so it wants to pull in an electron, and therefore it takes the electron away from lithium. And lithium then loses its second orbital. So you notice how they both have filled their valence orbital. Fluorine has 8 electrons in its second orbital. That's a full octet in its valence orbital. And lithium lost that electron in its second orbital and lost the second orbital. So now it has a full valence orbital, which is now its first orbital. So the negative charge and positive charge are attracted to each other to form a bond. This is an ionic bond because it is formed by two ions. So lithium is a positively charged cation, positive cat, because it has one more proton than electron. Fluorine is a negatively charged anion, negative ant, because it has one more electron than proton. Notice that ionic bonds follow the octet rule. Lithium's valence orbital, which is now its first orbital, is full. Fluorine's valence orbital is also full. So both are at their most energetically favorable state. And again, we metaphorically say they're happy, but you don't want to use that word on the AP exam. Energetically favorable state is the best way to express that. So in ionic bonding, alkali, alkaline earth, or transition metals, those are the weak guys, send an electron over to nonmetals, those are the strong guys. So these guys over on the left, and it can be also the transition metals, they send an electron over to the strong guy. Strong guy takes the electron away. This makes the alkali, alkaline earth positive and the nonmetal negative so that they attract each other. So ionic bonds happen between a metal and a nonmetal. The high electronegativity of the nonmetal pulls on the electron of the metal. The low ionization energy of the metal means that it easily gives up the electrons. The electron is passed across the periodic table from left to right. That's just figuratively speaking, it's passed across the periodic table. Really, the two atoms are right next to each other. The metal, the weak guy, loses an electron and becomes a positive cation. The nonmetal, the strong guy, gains an electron and becomes a negative anion. And the cation and the anion become friends and are attracted to form an ionic bond. So I've shown this concept, you see, in several different ways. The idea is that some of these visuals will stick in your mind. So I've given you the same explanation about 3 times. So using the charge numbers of ions in 60 Commons ion sheet, and you will not have that sheet in your hands when you do this assignment, but you'll have it soon enough by the end of this week. Use the crossing arrows method to assign the subscripts, remove any negative signs, reduce the subscripts if they have a common factor. So let's do a couple of these, and you can just look at your periodic table, and you notice that sodium is in the far left column, alkali metal, so it has a +1 charge. It easily gives up an electron. Bromine has a 1- charge. It's in the halogens. It's right next to the noble gases. So you should be looking at a periodic table in your book, or if you don't have your book, you can go online and just pull up pretty much any periodic table. So sodium likes to give up an electron to become like a noble gas. Bromine likes to take in an electron to have a full octet and be like a noble gas. So sodium is a +1, bromine is a 1-. And so what you do is you crisscross those two numbers. So you take the 1 from bromine and put it as a subscript for sodium. You take the 1 from sodium and put it as a subscript for bromine. In other words, you're trying to get these to match up so that they're electrically neutral. And you see there, this is a pretty easy one. It's a +1 and a -1. They match up. They balance each other out, and they're electrically neutral. So that forms NaBr. It's Na1Br1, but when you have subscripts of 1, you don't write them. So K and O, potassium and oxygen. So if you look at the periodic table of charges, go back a few slides, potassium has a 1+ charge. It wants to give up 1 electron so it can be like the nearest noble gas, which for it would be neon. Oxygen wants to gain 2 electrons. It wants to add 2 electrons to be like the nearest noble gas for it, which is also neon. So oxygen gains 2 electrons. That makes it a 2- charge because it gained 2 negative charges, whereas potassium lost 1 positive charge. But so how many potassiums do you need to balance with the oxygen so that they're electrically neutral? Well, you need the same number of pluses as minuses. So you would need 2 potassiums, that's the K, 2 potassiums, 2 times 1, to be equal to the -2. And the way you simply do that is you use the crossing arrows. So the 2 goes down in the subscript of the potassium, and the 1 goes down in the subscript of the oxygen. You remove any negative signs you see there, and you have K2O. So again, potassium K has a +1 charge. If you have two of them, you have a 2+ charge. A single oxygen has a 2- charge, so 2+, 2- balance out. They're electrically neutral. Try another. How about beryllium and selenium? Well, if you go to the periodic table, beryllium is an alkaline earth metal, so it takes on a 2+ charge. Selenium, if you look at the periodic table of charges back a few slides, it has a 2- charge. So if you do the crisscrossing arrows, you end up with Be2, Se2. Again, remove the negative sign. But it's kind of like a fraction. You can reduce it. If you have 2 berylliums for every 2 seleniums, you can just reduce that down and say that you have 1 beryllium for every 1 selenium. So those are balanced charges. The charges have to balance. That's the whole key to this exercise and how you put together ionic bonds. Finally, iron and nitrogen. Now, iron is a transition metal. You'll remember that it can take on one of 2 charges. If you don't remember that, and you don't need to, go back and look at that periodic table of charges. So iron can either be a 2+ or a 3+. So which one matches up with nitrogen? It could be either one. Nitrogen is a 3-. So we're going to say it's iron with 2+. And nitrogen has to have 3-. Nitrogen only has that 1 charge. Nitrogen wants to take on 3 electrons to fill up its octet and be like the nearest noble gas, neon. Iron, the explanation as to why it loses 2 electrons, there really isn't one. You don't need to understand why it likes to lose 2 electrons or 3 electrons. You just have to know that it does by looking at the periodic table of charges. So the way you put this element together, the pluses and the minuses, the anion and the cation, is you just crisscross those numbers. So iron becomes 3 and nitrogen becomes 2. So what are you saying? 3 times 2 positive charges, a 2+ charge, will give you a 6+. Let me say that again. 3 times 2+ gives you 6+. And for nitrogen, 2 times 3- gives you 6-. So you have a 6+, a 6-. They balance, they're electrically neutral. So the crisscrossing arrows is just a simple way to know how to put 2 ionic elements together to form an electrically neutral ionic bond. Ionic bonds must be electrically neutral. They can't have a charge on them. Okay, so that completes our lesson on ionic bonds. Again, some of these lessons you may want to go out back, some of these videos, go back and watch them a second time. This isn't all going to come easily. It's not like watching a movie. You really need to kind of study it. And I'm going to have you write out some of these explanations as paragraphs, basically explain in a paragraph how an ionic bond works, okay? So in the next lesson, we're going to study the other major kind of bond, which is covalent bonds, and then we'll also study the third type of bond, which we don't deal with much in this class, and that's metallic bonds. We'll deal with that in the next lesson. So have a good day.